so we'll make do without them. So we actually have a very interesting lineup today. I think it's worth drawing attention if anybody left in the astronomy world who doesn't know that Gaia had its second data release. Yeah. And there are already people working on it here, so it's a very exciting time. But we'll be hearing in order from our own Pierre Christian. Then we'll be hearing from Kathrin Altwegg, who's a colloquium speaker later today. Alexie Leauthaud, who just gave the ITC colloquium. And then we'll finish up with our own Idan Ginsberg. So just to get started, I'd like to mention the Eric Tito Prize for graduate students in theoretical astrophysics, which was endowed generously by ITC senior member Eric Tito. And it's awarded each year for what's selected as the best thesis in theoretical astrophysics by a student at the CSA. The restriction on the nominated student, he needs to receive his or her PhD in the year of the award on a topic in theoretical astrophysics. So it's pretty broad. So just briefly give the floor to Eric, who can say a few words about Pierre.
Well, anyway, it's a great pleasure to have Pierre get the award. This is the 10th anniversary that we've been giving this award out. We started this 10 years ago. And Pierre is a worthy recipient. He's done several studies on the mass distribution in space-time around supermassive black holes, and showed how observations of pulsars and zero delays could test the Milgauss theorem, and some papers showing novel applications of LIGO and future LISA observations, and he's going to talk to us about another project that he's done on the interference of gravitational waves. So it's quite a record of accomplishment. And congratulations on getting a PhD and the award.
So thank you, Eric, for the kind introduction, and it's I'm honored to be the recipient of this year's Quito Prize. And I was told to receive the prize, I have to give a talk. So technically, I'm the only person who's actually paid to do this. Okay, and Avi's not here, but that's fine because he's seen this many times. So this is a project that I've done with Avi, and it's also done in collaboration with Salvatore Vitale, who is a professor at MIT. He's our connection to LIGO. So what we are talking about today is gravitational lensing of gravitational waves. And in particular, I want to start with, kind of a description of what is gravitational waves, just to get everyone on the same page. So in general relativity, gravitational waves is a perturbation upon the metric. It's a ripples in space-time. So if you have some metric g mu nu, you can split that into some background component, g mu nu background plus h mu nu. So this is a small perturbation, and this could be anything. It could be your Schwarzschild, your Minkowski, pick your favorite metric, and then you can add an h mu nu on this, and you just do perturbation theory. Okay, so in words, space-time is just some background space-time plus some gravitational waves. Okay? So you can compare this to the ocean. The ocean is calm water plus a component that's ocean waves. Okay, it's just basically mostly like a thing, and then you have a perturbation upon it. Okay, so I know not everyone works in this subject, so it's usually easier before that. So to talk about gravitational waves, really what we are talking about is this, h mu nu. So whenever someone says gravitational waves, what they mean is this, h mu nu, this small perturbation. Okay, so in order to make it more kind of like visceral for people who are not in this field, you can think about our more familiar example of electromagnetic waves. So if you have electromagnetic waves, it's some vector. This is a wave in the z direction, Ex, Ey, and a 0 here, and then you have this exponent term that makes it wavy. Gravitational waves is exactly the same, except instead of this vector, you have a matrix, a 2 tensor. And again, all the z components, this is going in the z direction, all the z components are 0, and then you have these other spatial components. Much like electromagnetic waves, which has polarization, like this E has a Y polarization and X polarization. Gravitational waves also have two polarizations, plus polarization and cross polarization and everything, So really, you just think about these as electromagnetic waves. If you are not, if you're not familiar with the formalism, it's perfectly fine. You just think of these as standard electromagnetic waves. Okay? So, now, if they are really like electromagnetic waves, then there is a natural question, which is, these things, they bend when they pass a massive object. This is called a lensing event. So the natural question is, does H bend? Is this also a thing that H do? And turns out the answer is yes. In fact, H acts like almost any other waves to zeroth order. Okay? I can split H mu nu, which is a tensor, this matrix, into a component that looks like this. I take out a scalar component, I call it phi, and then I multiply it by the rest of the, the things with the little indices. This is called a polarization tensor. And if you just plug and chuck into the Einstein equation, what you get is phi actually follows the equation for any other waves. This is, box phi equals 0. It's an equation for any other waves. One caveat is that this box is the D'Alembert for the background metric, not for the full metric, which includes H itself. This is because we are only solving H to smallest order. Okay, so this box is the box for the background spacetime. But once it's in this form, it's very familiar to solve it. In fact, you can solve this using the Fresnel-Kirchhoff integral to solve this equation, and you yield a magnification factor, which I call F. And I define this as phi lensed over phi unlensed. It just tells you the magnification factor if you get lensed by this object. And I've implicitly switched to Fourier space. So now everything there's like an omega in there, but this is familiar from electromagnetism. This integral requires some elaboration. What is this t? So this t here is a function that depends on where the source is, where the observer is, and the background spacetime, just like in lensing of electromagnetic radiation. The background spacetime we are using is an expanding universe with Newtonian potential U. Okay? So the way to think about this is a combination of an FLRW metric. This is your familiar one. Okay? I've taken a square out, so I need to switch my time from t to eta, the conformal time. But everything else is fine. This is the metric that the wave propagates in for most of the journey. And then there's a weak field metric. You can think of this as small curvature limit of Schwarzschild that looks like this. Okay? This just tells you where my big masses that can lens things. So yeah, I can just combine them and it looks like that. Okay? Right, so now, here's the problem. In gravitational lensing of electromagnetic radiation, we are used to working in the geometric optics limit. What this means is instead of waves, we think of them as just like vectors, just little lines, and the lines get bent. However, from the Fresnel-Kirchhoff integral, this is only valid when the length scale of the lensing potential is it's much larger than the gravitational wavelength, than the wavelength of the radiation. Okay, so we can define a dimensionless frequency parameter. Okay. This is just basically a ratio, if you do like a 1/, this is just a ratio between the length of the lens versus the length of the wavelength. Okay? And if this is much larger than 1, then you can use geometric optics. However, for a frequency of 100 Hertz, and for a lens mass of 100 solar masses, turns out you are in the wave optics regime. So for LIGO, stellar mass lenses are in the wave optics regime. So our intuition of geometric optics cannot be used in this regime. But that's fine. You can just do the integral, and then you get a magnification factor that looks like this. It's a function of all these things that we know of, and in particular, it's of course a function of the impact parameter. Further away from the lensing potential, you expect smaller amplification. Okay? The signal in frequency space is simply given by a multiplication of the observed signal and the amplification factor. It's just magnification times the observed signal. Okay? Sorry, amplification factor times the waveform, the unlensed waveform, that will be your observed signal. If you take limits of this, when omega is large, you go back to geometric optics. Here you have two images with a time delay between them. Okay? So you take lensing mass of, a cluster, for example, you get geometric optics. Right, so what does this amplification factor look like? The real part looks like this. Okay? So this is a plot for different impact factors. Like this is for if the beam is going close to the lens, and this is for when the beam is going far from the lens. You see, if it's close to the lens, it looks pretty much linear. However, as you can probe more and more of this function, it actually looks like a sine wave. It's this is the whole this is the whole point of doing this diffraction integrals, because you can get this type of sine wave. And if you have a really large impact factor, the amplitude of the sine wave gets smaller and smaller and smaller, and it becomes basically one. Basically, you don't get change. Right. So, how do we find lenses in LIGO data? It's actually quite simple. So we added this f omega to the model, or to their waveform model. And this is quite natural to do because LIGO actually has all sorts of mechanism that allows you to modify the waveform in order to find extra parameters. For LIGO purposes, this is usually done to search for, post-GR correction, stuff like that. But for us, we can reappropriate it to find lenses. So we ran the parameter estimation code for a variety of signal-to-noise ratio. And for each signal-to-noise ratio, we put in a lot of different masses. This is an injected event, so we inject lenses into this code and see if they can find them. Okay, and then we compare the fit against model without lensing using this odds ratio, which is a ratio of the probability of the code finding a lens versus the probability of the code finding no lens. So if the code can find a lens, odds ratio is larger than 1. So this is the result. If you have a high signal-to-noise ratio, of course, you can detect smaller masses. You can detect smaller lenses. However, for parameters that are, seems there's some time dilation. For parameters that are relevant to LIGO, it turns out that the smallest lens that is observable is probably only a few tenths of solar masses. Okay, and this is it's pretty good, but there's not that many few tenths of solar masses of bodies in the universe, so we want to go better. If you go to 3D detectors, your signal-to-noise ratio can get improved to 3,000, much higher. So this is a posterior PDF for the lens mass. I'm just trying to show that 3D detectors are sensitive to lenses as small as 1 solar mass. Importantly, 0 is excluded here. Okay, so I don't have time to talk about rates, so I'll just skip that. So here's my conclusion. Stellar mass objects, they lens gravitational waves in the wave optics regime. So this is unlike lenses in electromagnetic theory, which usually lenses in the geometric optics regime. Current generation detectors are limited to really massive lenses, really like 30 solar masses. However, 3G detectors probably would allow detections of lenses up to, as small as 1 solar masses. And I need to make a plug here. If you want to hear more about black holes and gravitational waves, my public talk for my dissertation is next Wednesday, 9:30 a.m., bright and early in this room. It has way less math. So if all those, all those equations are kind of boring, then it's a public talk. Yeah. Thank you. Yes.
Do you have to be concerned about the propagation of polarization? Polarization can rotate.
Yes. Yeah. If you see, I split H mu nu into phi times the polarization, completely ignore the polarization. So that's something that, haven't been done yet. The kind of the order of magnitude or the, envelope calculation, it seems that polarization doesn't change much, but more work needs to be done for that.
You haven't said much about what these lensing objects would be, but if it were a black hole, is there any signature that you would expect in the gravitational wave that would be affected by the spin of that black hole and its orientation?
Yes. However, you need to go close to the black hole. Right? So if you remember, our lensing metric is using Newtonian potential. So a black hole in, like you can put black hole in cosmology, you have these metrics which are, like black hole in de Sitter spacetimes, and it has all the things that you want. And the lensing, of course, changes because of the propagation in this metric, but you need to get close to the background, to the hole, to really get something that's observable.
I'm just curious what kind of time delays you get out of this if there were an EM signal as well, or from, do you have a different?
Oh, for the EM signal?
Well, for the gravitational waves, is there?
So this one doesn't really have a time delay, right? Because in the wave optics regime, you just get diffraction patterns instead. Once your masses are becoming larger and larger, you started to get these like what could be called as a time delay. And for a cluster, the time delay could be months. So you can get like for a lensing with a cluster, you can get an event, and a few months later you get another event that's slightly smaller. So.
Yeah, you didn't mention the statistics, but so is this important enough so that in fact most of the things that you see are actually lens, or is it just something that you see from time to time?
This is something you see from time to time. In fact, we run the code on the LIGO data, like the ones that they found, and we couldn't find any lenses. So, yeah, they have good eyesight, no need lenses.
Okay, good afternoon, everybody. I'm very happy to be here. I will not have time in my colloquium to talk about the landing of the Rosetta lander, and that's why I give a short introduction here on landing and also the pros and cons of landing, sample return, and just measure in situ. That's Comet 67P. As you probably have seen it, to land on such a body is definitely not easy, as we all know by now. It's not because of these uneven parts of the comet, it's because of the gravitation, which you don't know. So you have no idea how the gravitational lines work. And that's the lander here. It's about 1 meter size in all dimensions, and it's a completely passive landing. So it was just dropped from 22 kilometers to the comet. It took 7 hours to go down. The comet has a rotation period of 12 hours, so it turned around by more than 180 degrees. That's the landing as it was seen by Rosetta from above. And you see we have different pictures. At 1514 it was here. So it's an enlargement here of this picture, and you see the lander. 1519 it was here. It looks as if it goes sideways, but that's because the comet turns underneath. 1523, and the landing was at 1534. We don't have a picture at 1534, but we have one at 1518 of this location up here, and we have one at 1543. And if you look carefully, you see the difference. You see the 3 footprints here. So that's where the lander landed, and it actually landed exactly at the spot where it was supposed to land, within 100 meters, which was quite an achievement for flight dynamics. But it didn't like it here. It had 2 harpoons to put it on, to keep it on the surface. They both didn't work. It had a thruster to put it down, it didn't work. So a triple failure, and the lander was gone. And this picture here at 1543, the picture was much larger, and you see it here. That's the lander flying away. So it's not easy to land on such a body. And it was later reconstructed. It landed up here in the summer hemisphere. No, it's not a hemisphere, it's a hemiduck. Summer hemiduck of the comet. It jumped, it hit its head here, turned around. We know that from the magnetic field measurements. And then it hit again here. And then with a last hop, it went into a ditch. Which was quite unfortunate. And this here is the winter hemiduck. So it jumped from summer to winter. Very late in the mission, 1 month before the end of the mission, we found it. It's here in the ditch. It's clear, it's the lander, and it's on its side. And of course that poses some problems for the science to be achieved with the lander. What did we, was it a failure, was it a success? Probably both, a little bit of. But the most important results, we didn't detect any intrinsic magnetic field. This could very well be measured by the magnetometer on board of the lander and together with the magnetometer on Rosetta. We also found out that the comet has a very porous structure, 75% of nothing. And it's very homogeneous. As far as we can say, it's very homogeneous down to 10 centimeter scale length. And of course, you get the closest ever images of the nucleus surface. And that was the good thing about the hopping, you see. The surface is very diverse. So the first picture was regolith. The second picture seems to be something much more solid. What we missed, because it was lying on its side, we could not drill into the comet, so the nucleus interior composition we didn't get. Tensile strength, thermal conductivity we didn't get really, and we still don't know how a comet works. Now, would it be much better to do sample return? We already have a sample return. That's Stardust, which brought back grains from Comet Will 2. And they got very nice measurements of the mineralogy of the refractories, but only the non-organic grains. They got the detection of these hot phase CIIs and also the amino acid glycine. What was not optimal, I would say, is that all organics were more or less destroyed upon impact. The impact velocity here was 6 kilometers per second. Into the aerogel gel, which is a good material, but of course it's still too much energy being dissipated. And then they had a lot of contamination issues on Earth. So they detected many amino acids, but only glycine. They could confirm that it's cometary. All the others are probably terrestrial. So the next sample return mission, which is planned, which is now in a phase A, that's Caesar. It will go to the same comet as Rosetta, which is on one hand good, because we know already a lot about Rosetta, about this comet 67P from Rosetta. But on the other hand, it's very bad, because if they don't bring the sample back, the result will be 0. We won't have learned anything else. Now they want to bring back a sample. They grab it, they put it in a container. They have a second container where they will capture everything which comes out of this sample and keep it as volatile but non-cryogenic. So I would say detailed mineralogy of dust, including this time the organics. That should be feasible, and that will be great. Probably the precise isotopic measurements of many isotopes will be feasible, but only atomic, because bringing volatiles back, you have a lot of time to do chemistry on the way back. You know, if you do it non-cryogenic, you have a lot of radicals in the comet volatiles. So will it be pristine? Probably not. And then upon re-entry, we have seen 75% porosity. It's a very fluffy structure, and the dust is fluffy. You see that's a dust grain after impact with 1 meter per second. Not 6 kilometers per second, just 1 meter per second. That's a picture from Cosima, the Cosima instrument on Rosetta. So the relative velocity there was 1 meter per second to the dust. And almost all of their grains looked like this, just heaps of sand. And I guess if you have to decelerate a capsule with 40 Gs, not much of the structure will be preserved. So the structure will most probably be gone, and you will again have contamination issues. Because you have material, you have terrestrial material around it, you cannot avoid it. So it will be a good mission, but it will not solve all the problems, that's for sure. Or should we do a cryogenic sample return mission? That's probably for the future. It's technically not that easy. And you still have to solve these problems. From which steps do you have to get the material to have pristine cometary material and not just regolith? Then at what temperature do you have to sample it and bring it back? 20K? 10K? 30K? And then when you sample it, how do you preserve the structure, the stratigraphy? That's definitely not easy to solve. And again, the re-entry is almost impossible to do without destroying the sample. And we will not be able to answer this. The heterogeneity, of course, we will not be able to answer heterogeneity of the comet because we will sample at one, maybe at 2 places on the comet, but not more. And also the evolution of the surface we will not be able to see. So I actually like in situ, but I like even more. I like sample return, but I like even more in situ missions, and I think that's what we should do, because then you don't really have a lot of contamination, and you can be there, study it in detail at different places. So go to another comet, not 67P. Take a comet which has a different D over H, and then stay and hop on the comet if possible. dig, do in situ analysis of dust and volatiles. We now know how to do that, and analyze the stratigraphy and observe the activity from close up. So that would be my next mission if I could choose. Thank you very much. Before 24, or when will the space station die? Yeah, but even for the space station you have to decelerate. You will not warm it up that much, I think, because you don't go through the dense atmosphere, but you have to decelerate. And as far as I know, it's about 40 Gs. It's a lot. It's a lot.
What are the science cases that can only be done from the ground and cannot be done in situ?
I think very precise isotopic measurements, especially of the refractories, like strontium and things like that, age determination.
Take one more from Martin.
You must have learned something about the surface strength of the material from the bounce.
We thought so, yes. The first place where we landed, it's clear that there was regolith, probably 10 centimeters of regolith. So we don't really know what's underneath. The second place we didn't bounce, or only very little. And then it was on the side, so yeah, it hammered. You know that there are papers, if you read in the literature, it tells you that there are megapascals. Because it hammered, and it never entered, but it hammered like this instead of like this. But we knew that only very late in the mission when we saw the position of the landing. Thank you.
Is there a, oh, here it is, okay. So I got to talk about hyperstream science this morning, and for this venue I wanted to take advantage of the short format to talk about something a little more lighthearted. This is a side project I'm working on. It's also under development, so that's why I can summarize it in 10 minutes. But it's incomplete, and if you're interested, come and talk with me. I'd love to hear your opinions on this. Oops. So I'm going to talk about blended galaxies, and a blended galaxy is something that happens in an imaging survey where you have two galaxies that are in front of one's in front of the other, and your detection algorithm, source extractor or something else, detects them as a single object. So if you're working with images from Sloan, so this is a Sloan image, you may not be so concerned because galaxies look relatively far apart. There maybe aren't so many blends, maybe one down here. But when you go to deeper images, this is from the HypoSupremecam survey, you're going to be more affected by blends between galaxies. And the LSST survey, starting in only a few years, is going a magnitude and a half deeper than this. So why do I care about blends? I study gravitational lensing. And as blends become more important, you might ask the question, what is the shear of a blended object? Maybe that's not too difficult of a problem if galaxies are at the same redshift. If you're blending galaxies from different redshifts and measure the shear, what are you measuring and how is that biased? Also, what is the photo-z of a blended object? So as we go to high precision lensing measurements, these questions are coming more to the forefront. And there's a new working group in the context of LSST that is studying these questions in greater detail. It may become one of the systematics that we need to tackle. So before tackling these questions, I want to ask, what is even the rate of unrecognized blends? What is the level of this problem? So an unrecognized blend, I'm going to define as two galaxies that are in projection that the blending algorithm has failed to detect as two galaxies. So there are three approaches that you could consider to try to quantify this ambiguous blend fraction. One would be direct simulation. So fully forward model the process, build a full simulation to study this, and indeed LSST is doing this. It is quite tricky though. You have to get all the sizes of your galaxies correct and their magnitudes correct as a function of redshift. It's clearly not a trivial problem. You could do a hybrid approach. This is something we developed in the context of the Hypus PrimCam survey on Subaru. We took real HSE galaxies and injected synthetic galaxies into these images to study the blending properties between real galaxies and synthetic ones. It's kind of a hybrid. But in the context of developing this project, I came up with a sort of completely empirical approach that we've been developing, and that's what I'm going to talk to you about today. So the basic idea is based on studying cross-correlations. So this is the basic idea. Consider galaxies of different magnitudes, blue galaxies and green galaxies, and look at the angular cross-correlation between the green galaxies and the blue galaxies as a function of theta. So people like Daniel Eisenstein like cross-correlations or autocorrelations, but study them on scales way over there to detect a BAO. I'm proposing to look at this on scales of a few arc seconds, and then what you see is that this cross-correlation is kind of flat, and then suddenly there's a big dip here. And the reason this dip happens is because you're failing to deblend galaxies. So the simple idea that we were playing around with was measure this cross-correlation, extrapolate it, and predict how many galaxies you should have seen, compute this little integral, and this is going to tell you how many galaxies you're missing. So I loved this idea because it was completely empirical and easy to do, and might just give you a direct estimate of the blended fraction between these two types of galaxies. So I had a student working on this and came up with a plot of magnitude, one of the pairs of galaxies versus another magnitude, and computing the rate of unrecognized blends. It's low between bright galaxies and high blending fraction between fainter galaxies. But there's no color bar on this plot because we did a variety of simulations and found that this didn't work. So does anyone care to guess why it doesn't work? Because it seems like a pretty simple idea. I'll offer a blender to anyone who can guess. That's a joke. Any guesses why this simple approach might fail? It took us a while to figure it out, but we figured it out. It has to do with magnitude boosting. So if you blend two galaxies together, you detect a galaxy that is brighter. And we did some tests. It turns out that within the context of our particular pipeline, the magnitude of the blend is the sum of the fluxes minus 0.1 mags. That's a very good approximation, the magnitude. So let me re-go through this problem in a very simplified universe. Two galaxies. This simple universe would be great for simulators, only two kinds of galaxies. So we're going to have small black galaxies and blue galaxies. And then every now and then they blend and you get an orange galaxy. So when I study the unrecognized blend fraction, whenever I see a blue galaxy, it will have 0 blends. But when I see an orange galaxy in the simplified universe, it'll have 100% ambiguous blend fraction because the orange ones have only formed from the blends of these two kinds of galaxies. So when I study the cross-correlation between blue galaxies and black galaxies, what it is actually telling me is the number of times that I've got a blend of magnitude orange. And that's the thing we failed to realize in our first little calculation. So this is how far my student got. My student's now moved on to new horizons. So I'm looking for someone to follow up this project. If anyone's interested, by all means, come and talk with me. Moving forward, there are two things I would like to do. So now that we've realized that there's this magnitude boosting going on, and that conveniently, it turns out that when you create a blend, the measured magnitude is roughly the sum of the two fluxes minus 0.1 magnitudes. We can do the following. So we can use this cross-correlation method to try to directly estimate how many blends have occurred. So for galaxies of magnitude orange, go back and do the cross-correlation between all pairs of galaxies with fluxes that sum to orange, and do an integral here. So there's some 2D plane of cross-correlations that we need to go and study and do this integral and see if we can completely empirically recover the unrecognized blend fraction. This would be a backward model kind of approach, and I want to use simulations to see how well we can recover this. If it turns out for some reason, maybe scatter or some other reason that this backward modeling is complicated, the other aspect that I want to look into is more just so measuring all these cross correlations in real data. And I mentioned that there are efforts underway to build full forward models of image simulations for LSST. We can go back and compare the simulations to these kind of cross correlation measurements on very small scales. And this will be very, very constraining for the simulations, because to get this drop accurately, you really have to have the sizes and the magnitudes of the galaxies in your simulations correct. So we can either backward model it and measure it completely empirically, or we can also use this idea as sort of a strong constraint on how to tune up the simulations. So that's the basic idea. This is as far as we've got, and maybe some more progress next time. So something that someone in this audience is going to ask me is, we have beautiful images from HST. Why don't we just use HST imaging to understand our blend fraction? I did a lot of work during my PhD with HST, so I'm quite familiar with this data. And let me tell you why this doesn't work. So several reasons. The blending depends not only on the size of your PSF, it depends on the sizes of your galaxies. If you have galaxies that are really big, it doesn't matter if you have a really small PSF. If they're close together, their light profiles are going to be blended, and it's going to be hard to deblend them. So it's not just a question of your point spread function. So better PSF doesn't automatically guarantee better deblending. We played around with doing this with HST, and what you find is, yes, HST does a little bit better deblending, but it starts to lose, thank you very much, thanks to lose galaxies on scales of about 0.9 arc seconds, and the PSF is about 0.12. So the sizes of galaxies are also limiting the blending here. And furthermore, you see this peak. Nasty peak shouldn't be there. I think what's going on is actually sometimes in HST you can over-deblend. These kind of spirals can be very tricky. You detect these star formation knots in your deblender. So should really go and say something nasty to the person who made this catalog. That was me. Yeah, for my PhD I made this catalog and probably over-deblended. So it's not completely trivial. But I think we don't need HST. I think we can do this directly for your favorite imaging survey. Mine currently is HyperSupremeCam. So does it blend? Yes. Galaxies blend on the sky as we go deeper, LSST. The W first, this is going to become a much more pressing question, especially in the context of gravitational lensing. How often is yet a question to be answered, but maybe there's a completely empirical approach or something that cleverly intermixes empirical and direct simulation. Thank you very much. Yeah. Yeah.
So do you have to worry about that here? I mean, your orange blob,
yeah.
probing not just the sum of the fluxes, but some of the contributions.
Well, so yeah, absolutely. Yeah, we didn't take into, when I said sum of magnitudes minus 0.1, there is no accounting for dust there. That's something that we could go back and test with the direct simulations. That came out of the hybrid simulation approach where there's no accounting for dust. You're absolutely right.
So similar to the HST
Yes.
images that have multiple knots and
Yes.
that can mess up your blending.
Yes.
What about mergers?
Yes, so at the depths of LSST, most of the blends are going to be things that are actually uncorrelated. So there will be the question of merges, and is that one galaxy or two galaxy, but I suspect it's small compared to the blends just due to galaxies at different redshifts. Yes, but yeah, good question.
So does gravitational lens magnification
I guess it must do a little bit, yes, but yeah, you would expect that pairs of galaxies that are closely blended would have some magnification. You're absolutely right. The simulations that we did don't take that into account at all. So maybe there's even a slightly larger boost due to lensing. Yeah, that's a good question. I should look into that. Thank you very much.
Idan, Ginsberg, and talk about Gaia and globular constellations. I'm wondering how much have you got done
All right, everybody can hear me? Yeah, so thanks everybody for staying until the end. So I'm going to talk about globular clusters, globular cluster ages, and Gaia. I'm not really going to talk about Gaia per se. I'm kind of surprised I'm actually the only person who's sort of mentioning Gaia today. But this paper didn't start off as a Gaia paper. It just ended up this way. I'll explain why. But first of all, have to acknowledge all my awesome colleagues. Of course, everybody knows Avi and our ITC postdoc Sonak, who really led much of the study, and for really putting so much effort. He gets to sit down and eat while I'm talking. So, all right. So a little bit about globular clusters, just a background. All right, so globular clusters have about 10 to the 5 stars. They're very compact with the half-light radius is about 2 parsecs, although it can be substantially larger. So if it's larger, it's more diffuse. If it's a smaller half-life radius, it's more compact. You know, in the Milky Way, there are about 150 confirmed globular clusters, mostly above and below the plane and around the galactic center. But in the past, there could have been many, many more, perhaps even a few thousand. So globular clusters are primarily useful because of the age estimates that they provide. And they're typically very old, 12 gigayears, maybe older. But the youngest go down to 6, which I guess isn't that young, but they do vary from about 6 to basically almost the age of the universe. Now, also, my shameless self-promotion, we recently published a paper in gravitational waves, but that's not what I'm going to talk about. What I'm going to talk about is the work we've done, which is basically, the initial idea was, okay, so let's have globular clusters just dynamically evolve throughout, history around the Milky Way. What's going to happen? So we took basically a dark matter potential. We added in a disk, which is important because as the globular cluster passes through the disk, it becomes shocked. And we evolved a halo from z equals 127 until z equals 0. So that gives us our potential for the Milky Way. Then we need to do the dynamics of the globular cluster itself. And to do that, we use the n-body code by Sverre Arseth. And for profile fitting, we use the King profile, which is universally known to be a good fit for globular clusters. All right, so basically just the idea is you put the globular cluster somewhere, and you see it evolve over a long period of time, over gigayears. So the typical mass we use is 10 to the 5, and we varied a few parameters, including the initial position of the globular cluster from the center of the Milky Way, as well as the initial velocity that the globular cluster have, and a few other parameters which you can read up in our paper. It turns out it didn't really make that much of a difference, but when we did run this, what happened? Well, we got these nice tidal streams. So we can see the globular cluster here. We're following the center of mass of the globular cluster. We're going to see it evolve over long periods of time. And it's pretty. That's why I'm showing it to you. I think this initial globular cluster was, the initial position was 35 kiloparsecs from the galactic center where we started it. All right, that was fun. Okay. So you have all these tidal streams produced. Can you see any of the streams? That became the question. So obviously, what instrument might be able to see some of these stars that are out there from these tidal streams? And the obvious answer was Gaia. Okay, so this is a magnitude limited all-sky projection. So basically, if it's in color, Gaia should be able to see it. If it's in the background, if it's dark, then Gaia can't see it. Now, we realized that once these stars are no longer tidally bound to the globular cluster, then their motions are completely, they have free motions. So, okay, perhaps we can get the ages of the tidal streams. And we think we can, simply from the dispersion in the position and the dispersion in the velocity. Okay, so with that, we should be able to get the age of when a tidal stream forms. Okay, so from our simulations, we know exactly when a tidal stream forms because we have all the data in the simulation. But how do the proper motions, do they agree with the simulations or not? In other words, is this a good, probable technique for determining the ages of tidal streams? That was the question, and we think it is. For example, in one of our cases, we determined that the look-back time for this particular stream, and these are the tracer stars that are observable by Gaia today. The look-back time for this tidal stream is actually 3 gigayears, roughly 3 gigayears. So this is when the tidal stream formed. And if you just follow the proper motions, depending on if you consider the tidal radius to be 5 RT or 2 RT, there's some discrepancies in the literature. But somewhere in between there, you get anywhere from 2.52 gigayears to 1.92 gigayear. So it agrees within reason. It actually agrees quite well. In fact, if you plot all our simulations, so we have the proper motion and the actual look-back time that we know. So if this was perfect, it'd all be exactly lined up. But as you can see, it's really not so bad. There are, of course, error bars, both in the vertical and horizontal axes. So it's not perfect, but it agrees very well, better than we suspected initially. And so why is this important? Well, first of all, it's just kind of neat, right? It's neat, but it actually has some significance. And the proper motions can tell you the epoch at which a tidal stream was formed. So perhaps if we can see a number of these, we can start putting together when these tidal streams formed. Was there an epoch in which more tidal streams were formed, more globular clusters existed? That's the basic idea. Secondly, the dispersion in the position and velocity is just a good estimate of how long a star has been outside the tidal radius of the globular cluster. That sort of relates to my first point, but that in itself could be interesting to people that study stars. And lastly, it gives you a lower bound on the age of the globular cluster itself. So with that, what's the next step? Obviously, the next step is for people that actually really use Gaia to go out and look for these. And that's it. That's all I had to say today.
So did you follow the evolution of the streams? I'm surprised that they were as well, surprised they were so well, they were not more spread out laterally.
Oh, yeah. Well, we were following in the center of mass. They actually do get spread out to tens, maybe even 100 kiloparsecs. So the streams themselves do get quite spread out. We're just looking at the center of mass of the globular cluster.
Do you need line of sight velocities, or can you just use a couple of motions?
That's a good question. You could probably, really you need the line of sight velocities, but you could probably do some sort of lower bound with the proper motions for sure. Right.
So there are some existing streams, right? Palomar 5 and Milky Way. Can you learn anything or put in a lower limit on the age of that from?
So I haven't looked looked into that, that's actually quite an interesting point. So we haven't looked into that. We just at this point, but you're right. That might be something worth looking into. If you're a referee, then you can.
Okay.
Go.
Going back to your point about the line of sight velocity, you can actually get a very incorrect estimate of the age by picking out stars, because you're seeing these in projection essentially in the stream. If you pick something which in projection looks like it's part of the stream, but it's actually not, that will really mess up your estimate of the dispersion and therefore of the age. And so what you can then do is you can essentially isolate the ones that are actually part of the stream by using just a phase-based cut of their distance and line of sight velocity, and that basically segregates out your candidates that are just interlopers along the line of sight versus ones that are actually part of the stream. So that's where they could be quite useful.
Can I answer? Yes, please. Go ahead.
Yeah.
I was just wondering, so the usual way in which the ages of these streams are estimated is by the length of the stream, because the evolution is secular. How does this compare with this method?
Well, the length of the stream here doesn't really matter. So in a sense, it's just it's a new way to determine the age of the stream itself. So this is what we consider a new technique. So it'd be interesting it would be very interesting though if you can see these to determine, the age of the stream, the traditional way, so to speak, and this new method, and see how they correlate. I think that would be quite interesting if you can do that.
Okay, well, let's thank all of our speakers.
They thought I was done. Oh, but then yesterday
On your great project.
He's the one to give the talk.
Yeah, did all the work.
How'd the talk go? Yeah, it was alright. Yeah. Got the information across, that's the main thing.
That is, yeah. Got some good questions too at the end. That was nice. Yeah.
Right, no one's saying this is complete bullshit.
Smile the most.
I didn't get the prize though.
Oh, well, but you're not a graduate.